All right. Hello, everyone. My name is Joao Vaz Carneiro. I'm a PhD candidate at the University of Colorado Boulder. And I just first like to acknowledge my co-author and advisor, Dr. Hans-Peter Schaub. So today I'm going to be talking about the backsubstitution method. I'm going to do a little bit of a survey and also talk about its capabilities and limitations. And the backsubstitution method is nothing else but a formulation or a way of writing the equations of motion. Um, that under certain assumptions gives us very powerful capabilities, namely very fast speed and modularity. But let's just jump right into it with the sort of prototype problem statement. So here we have a spacecraft. In gray, we have a rigid hub, and we really care about two states here. We care about the hub's linear acceleration, and we care about the hub's angular acceleration. So the linear acceleration is r double dot bn, and the angular acceleration is omega dot bn. Attached to the hub in blue, we have a few components, which I'll be interchangeably calling effectors. And these effectors can have one or multiple degrees of freedom defined by these alpha double dot. And the backsubstitution method assumes these two things. First of all, that all bodies are rigid. And second of all, that all components connect directly to the hub in parallel. And what I mean by this is that we don't really connect components to other components. We can only connect components directly to the hub. And if we want to create a more complicated or complex component, then we're free to do so, but we have to define the equation of motion for that particular component. Now let's talk about equations of motion. Usually in any mechanical system, we can write the equations of motion like this. On the left side, we have the mass matrix, which can depend on the system state vector Q, and we multiply that mass matrix by the state acceleration vector Q double dot. Now you'll see that in this case, we stack the hub's states, so R double dot Bn and omega dot Bn, and then we also stack all the other component states. So we have alpha 1 double dot up to alpha E double dot. And on the right side, we have the non-acceleration contributions. And what I mean by this is these are all the terms that do not explicitly depend on the state accelerations. They're still going to be force or torque-like terms, but they don't depend explicitly on R double dot Bn, omega dot Bn, or any of the alpha double dots. Looking at the mass matrix, we can sort of separate it into multiple parts. The top left is the hub-on-hub contributions. And then to the right of it, we have the effector on hub contributions, then the hub on effector contributions, and then everything else is the effector on effector contributions. Now we can further separate this submatrix into the cross effector contributions as the off-diagonal terms of that submatrix. And then along the block diagonal, we have the self-effector contributions. And the key aspect here is that using the backsubstitution method assumption, that is, that all components are attached to the hub in parallel, all cross-effector contributions are zero. And why do we care about this? Well, we care because our ultimate goal is to solve for the state acceleration vector. Because once we have a solution to r double dot bn, omega dot bn, and all the alpha double dots, we can plug those solutions into a numerical integrator, propagate them, and then we get a sort of time history for the system states. Now, the sort of simplest and most straightforward way to do this is to just invert the system mass matrix. The issue with this is that this is very computationally expensive. It scales on the order of n cubed, n being the size of the matrix. So basically, n is the number of states. And the key aspect here is that the unique assumptions of the backsubstitution method means only smaller submatrix must be inverted. So instead of us inverting one n by n matrix, we're inverting smaller 3 by 3 or 6 by 6 matrix, and that is much faster than inverting the whole thing. So let's talk a little bit about the capabilities and limitations. Why do we care and why do we go through this? The capabilities are clear. First of all, is speed. Cody Allard et al. In 2019 demonstrated that it's up to 8 times faster than a QR decomposition. So QR decomposition is sort of just a straightforward matrix inversion. And this is particularly useful for Monte Carlo analysis, where we have many simulations, and these simulations can potentially take a long time each. And so that speed increase is really noticeable there. The other important aspect is modularity. The consequence of this is that the contributions of all effectors are parallel. So we don't really have effector contributions on other effectors. And this leads to also modular testing. And what I mean by this is we can test a component or the equations of motion of a particular component A, and then we can test the equation of motion of a particular component B, and we would know that the system AB still behaves exactly the same way. And so once we find the equations of motion for one component, we can readily use them with as many other components as we want, as long as the equations of motion have been developed for those. Also, an important aspect of this is that data sharing is compartmentalized. So the effectors don't really share state or geometry information between them. That all goes through the hub, and it's a sort of the data sharing is between the hub and the effector. It's a two-way communication that way. However, there are some limitations. First of all, the development of the equations of motion is not straightforward. It actually takes a substantial amount of time to analytically find these equations of motion and also write them in this very particular way. And the other limitation is that the spacecraft configuration space is limited. What I mean by this is because of the assumption that all components are attached in parallel, some spacecraft configurations just cannot be simulated. And one of the things that hasn't really been touched on or sort of analyzed very thoroughly is how do we define exactly what types of configurations can be simulated? And this is important because we want to understand, well, is the backsubstitution method appropriate for the spacecraft configurations that I'm interested in? Because if it isn't, well, there's no bother in going through the development of the equations of motion. But if it is, we can extract those really powerful capabilities like speed and modularity for our use cases. All right, so to do that, to sort of understand the configuration space, we do this topology analysis through this graph theory. And so basically this here's an example of a spacecraft. Again, we have in gray a rigid hub and in blue the effectors, and we can sort of separate them out into their basic components, into their basic parts, where each part is then attached to another through joints. And then we can transform this into a graph. And once this is defined as a graph, there are a lot of algorithms and a lot of tools that we can apply to this to sort of understand what can and cannot be simulated. One thing that's important here is that when we construct a graph is basically comprised of nodes and edges. Here, each node corresponds to a part, and each edge corresponds to a joint. We can have weights to our edges. They usually denote degrees of freedom. But for our case, this is not particularly important. All right, so here are some examples of what we can and cannot do in terms of graphs. So this is just an example. This is totally allowable. So in this case, C would be our rigid hub. We'd have three components: component AB, component D, and then component EF. There are no branches apart from this, or just from C. No other nodes have branches. There's no loops. We're good. This, however, is not allowable. There's a closed loop here, so the assumption that the components are attached in parallel kind of breaks down for this. And this is also true for this example here where two forks exist. So it kind of forks out to two separate ways, and this is also unallowable. So I guess we can draw some examples of what we can and can't do, but can we really define an algorithm that describes whether configuration can be simulated or not? And the answer is yes. So the algorithm is here on our left, but the idea is that we were going to pick a random node as a candidate hub, or we call it a candidate base node. And from that, we're going to search all of its adjacent nodes. For each adjacent node, we're going to run through that chain, and if there is a closed loop, we can immediately stop the simulation because closed loops are not allowed. If there is a branch, we don't immediately exit because that is potentially a candidate node for our hub. And if we search through all adjacent nodes and we don't find any branches or any loops, then we're good. The search is successful. In this case, in this example, we don't really we kind of stop when we find the first potential base, but you can have an algorithm that sort of finds all possible candidate hubs and then picks the one that minimizes some quantity that you care about. For example, minimizes the maximum number of degrees of freedom of any component. So let's give an example here. So on the right side, lower right, we have an example graph, and let's start with candidate node A. So A has one adjacent node, B, and if we go through that chain, we go through B, that's fine, C, and that's fine, D, that's fine. But then at D, we see that it branches through E and F. So this is A could not be a candidate node. If we do the same for B, now we have two adjacent nodes, A, which is totally fine, and C. So we go through the chain of C and we get to the exact same problem at D where it branches out. And you might have found a solution already, but if we start with D, then we have three adjacent nodes. C, and that chain is completely fine. And then we also have E, which is fine, and F, which is fine. So in this case, this particular configuration can be simulated with the back substitution method if D is chosen as the hub or the base. So that's the basic idea of what this algorithm can do. It can sort of help define what the back substitution method can and cannot do. So let's talk a little bit about what's been done, what sort of contributions have been published on this back substitution method, because there are plenty. And please feel free to look at the paper for more information. I go into a thorough analysis of each component. What are the assumptions are? What their assumptions are? Why do we care? Why do we not care about that? So the first ones are the momentum exchange devices. So here we've defined reaction wheels and also variable speed control moment gyroscopes. So reaction wheels are 1 degree of freedom components. Variable speed control moment gyroscopes are 2 degree of freedom. And here the key aspect of this formulation, obviously using the back substitution method and obviously all its sort of benefits, but the key aspect here is that the formulation or the model is done in such a way that the spec sheet parameters can be readily plugged into the model. And namely, the static and dynamic imbalances are modeled as actual center of mass offsets and inertia tensor off diagonal terms. And so it is a very precise approximation that you can just readily take from the specification sheet. Hinged panels have also been modeled. Here we wanted to model two things. So first of all, sort of a rigid deployment where the panel can just sort of go from a stowed position into a deployed position. But also this method can be used to approximate first order flexing. And so if we attach a spring and damper to that hinge, we can approximate that first order flexing as long as we define the constants to approximate the properties of that first mode. Now, this formulation has been expanded to dual hinges, which again can be used for deployment or for first order flexing approximation. And actually, this formulation has been expanded to up to n panels. So we can have n panels. Obviously, the assumption here is that the hinges are always parallel. Another sort of extension on this has been the formulation of general rotating components. So here the key is whether that's for the reaction wheels and for the VSCMGs or for the hinged panels, we sort of made assumptions. We started with assumptions such as the geometry of the hinges, the mass properties of the panel, and from there we defined the equations of motion. Now, those equations of motion are great, and they are, but they're only can only be applied under those initial assumptions. So here, the goal of this generalization is to sort of remove those initial assumptions on the mass properties and on the geometry of each link, and to find the equations of motion of that. And actually, this has been found, the solution has been found for up to n degrees of freedom. So we can have up to n links, and each link has its own geometry and mass properties, and those are all general. No assumptions are made there. The only assumption here is that they rotate about a single axis each. All right, another contribution has been fuel slosh. So we have sort of the linear particle or spring mass damper, a linear spring mass damper approximation for fuel slosh, and then a pendulum particle, which also has a damper. These two are crude approximations of fuel slosh. Fuel slosh is a very complex behavior, but these are appropriate approximations. The linear particle more so for when the spacecraft is under constant thrust or constant acceleration, and the pendulum particle more so for rotational accelerations. We also defined the model for general translating components. So this is very similar to the rotating components, except that instead of rotating about an axis, they now move about an axis. And finally, we also have dynamic effectors. These are sort of the models that contribute to the right side of that equation that I talked about at the beginning. And there are a lot of environment models like gravity gradient, drag, SRP, and electromagnetic forces. We've also defined a very thorough thruster model, which accounts for the mass depletion and how the mass particles exiting the nozzle have an impact on the spacecraft motion. All right, and so to conclude, the back substitution is a formulation or a way to write the spacecraft equations of motion. It's fast and modular. And with the trade-off that defining the equations of motion is complex and there's limited configuration space. Now, this configuration space can be sort of analyzed using graphs and using graph theory. So we've developed an algorithm that runs through the graph and understands how or whether or not the system can be simulated in the backsubstitution method. And there's been an extensive list of models that have been developed for this. Feel free to look at the paper. We go into a lot of analysis and a thorough review of all that. And just as a sort of a extension of this, some of my colleagues are working on extensions to this. So I'm working on applying forces and torques to specific components, also prescribed components. So this is where instead of a two-way coupling between the component and the hub, there's a one-way coupling because the component is actually prescribed. All right, and I would just like to acknowledge my fellowship through La Caixa and LASP for also helping me out with this. Thanks.